So in the last class, we have started talking about support vector machines, and we have talked about some basic features of SVM, and then we have talked about the separating hyperplane support vector machines and how SVM works. That we also discussed, and finally we concluded with the decision boundary. So how decision boundary can be defined in a support vector machine, so that we have also discussed. So today we will see the parameter estimation and classification. So during training, we can estimate the parameters in SVM. So here parameters mean the model parameters. So your model parameters are weight vector and bias. Okay, so we see this problem as a primal problem, and we have to in this primal problem. So this problem is solved subject to some constraint. So you will see this constraint, how this constraint can be defined in SVM with hard margin and SVM with short margin. So we will see that later. But for sake of understanding the parameter estimation and classification, let us consider the primal problem. Here the primal problem is defined as L of W comma B. Okay, so here there are two parameters, W and B. Here W is the weight vector and B is the bias. So W weight vector is normal to the separating hyperplane, and this weight vector is responsible for orientation of the separating hyperplane, and bias is responsible for the location of the separating hyperplane. Okay, so here W and B are the two parameters. Here we have to estimate these two parameters. So we can get this primal problem, which is defined as W L of W comma B, which is given by half of W dot W. So here W dot W, instead of writing W dot W, we can write W transpose W. Okay, so both are found to be same. So half of W dot W minus summation, we get the summation over alpha I yi W dot xi plus b minus 1. Okay, so here actually we are getting yi W dot xi plus b equals to 1. This is the constant. So we can get this constant, which is multiplied with alpha. So here alpha is the Lagrangian multiplier. So for n number of training samples, so we can get this summation over this alpha I into yi W dot xi plus b minus 1, where alpha I is the Lagrangian multiplier. Okay, so whenever we find the extrema as minima or maxima, so using Lagrangian equation. So this Lagrangian equation is use the Lagrange multiplier, and Lagrange multiplier will help us to find the extrema as minima and maxima. So here in this primal problem, we have to maximize the bias and minimize the weight W. Okay. So now since this is the dual problem, so here we have to maximize the bias and minimize the W. So therefore, first of all, we will take the partial derivative of L with respect to bias B. Okay, so this partial derivative will give us the gradient of this function. So when you solve this partial derivative with respect to B, then this will give us this summation over alpha I dot yi equals to 0. So this is the solution when we take the partial derivative of L with respect to bias B. Okay, so this is the solution that we get after taking the partial derivative with respect to B. And in the next solution, so in the next step we will get the partial derivative. We will take the partial derivative with respect to W. So here we have to get the uh, gradient gradient of this function with respect to W, and finally here we will get, when you solve this equation, so you will get W minus summation over alpha I yi xi equals to 0. Okay, that means W, we can write W equals to summation over alpha I yi xi for I equals to 1 to n. Okay, so for n number of training samples. So when we perform the training, so we estimate these two parameters W and B. Okay. Now after estimating W and B, here we get W equals to this summation over alpha I yi xi. Now we have to put this to put this W, and here we have to get the 0 for this summation, and when we put these two when you put these two values in the original equation, this is the original equation, and then we can get a solution, okay, for this dual problem. Now for classification, what we do, we have to just find out the sign of this equation. Sign of this equation means if z is some unknown, sample. Unknown sample means the class level is unknown. Okay, so when the z is given, so here we get the W dot Z plus B. So W is known to us. So we have already determined the W from this primal problem, and we get the sign of this alpha I yi xi dot Z plus B. So this sign will decide whether this unknown pattern J belongs to positive class or negative class. Okay. So here Z is the unknown sample. So the class level of this unknown sample is not known or unknown. So we extract some features from this unknown sample Z, and here we get the dot product. Here we get the dot product of Z with W. So W is determined from this primal problem, which is nothing but alpha dot yi xi. Okay, so in place of W we are writing this, and this is making dot product with W, and this is plus B. This is the bias. Okay. Now we have to just find out the sign of this equation, and this sign will decide whether the Z belongs to positive class or negative class if we consider the binary classification. Okay. Now we will talk about SVM with hard margin and SVM with short margin. Now, when data is found to be linearly separable, and we don't allow any misclassification, then we use SVM with hard margin. Okay, so when the data is found to be linearly separable and we don't allow any misclassification, then we use SVM with hard margin. Now when a linear boundary is not feasible, that means the linear boundary is not able to classify the data linearly. So in that case we can allow some misclassification. So after allowing some misclassification, so we may achieve a better generality. Okay, and this is the that means here we can opt for the soft margin for our classifier. So short margin in SVM with short margin allow some misclassification, and generally the linear boundary is not found to be feasible in case of SVM with short margin. Now let us assume that the hyperplane separating our two classes, which is defined as W transpose X plus B equals to 0. We can also write W dot X. Okay. So instead of writing the dot product, we can write W transpose X plus B equals to 0. So this is the equation for the separating hyperplane, or the separating hyperplane, or the decision boundary. Okay. So this black straight line represent this separating hyperplane. Okay, and here we are getting two other parallel hyperplanes, so which are parallel to this separating hyperplane or optimal hyperplane. Okay, one is red color straight line, another is green color straight line. Okay, now if we consider that green color straight line belongs to negative class, positive class, and red color red color straight line which is parallel to the separating hyperplane, and there is only one support vector from negative class is found on the red straight line. Okay, now what will be the equation of these two parallel hyperplanes? If we get the distance from this separating hyperplane or optimal hyperplane, then the equations of these two parallel hyperplanes become W transpose X plus alpha equals to 0 and W transpose X plus beta equals to 0. Now what will be the distance from the separating hyperplane? If we get the distance of these two parallel hyperplanes from this separating hyperplane or optimal hyperplane, then the distance for the positive class becomes W transpose X plus alpha divided by mod of W. Okay, so here we get, this is the distance W transpose X plus alpha divided by mod of W. This is for the positive class, and for the negative class W transpose X plus beta divided by mod of W. Okay. Now, since we are not allowing any misclassification in the hard margin of SVM, so we want to maximize the distance between two hyperplanes. What are the two hyperplanes? This red and green. Okay, these two hyperplanes are parallel to the optimal hyperplane or separating hyperplane. So what we have to do? We have to maximize the distance between these two hyperplanes. Okay. Green straight line and green hyperplane and red hyperplane. So between these two hyperplanes, we will maximize the distance. So this distance is known as the margin. Okay, so we have to maximize the margin of these two hyperplanes. Now to find the distance, we can use the formula for the distance of a point from a plane. Okay, so what will be the distance? As I said, that the distance becomes W transpose X plus alpha divided by mod of W, and W transpose X plus beta divided by mod of W. Okay, this is for the negative class and this is for the positive class. Now what would be the total margin? So total margin becomes the absolute value of alpha minus beta divided by mod of W. So how we get this total margin? We get this total margin by subtracting the W transpose X plus alpha divided by mod of W. So here we subtracting the W transpose X plus beta divided by mod of W from this from the distance for the positive class, okay, which is W transpose X plus alpha divided by mod of W. So the total margin becomes absolute value of alpha minus beta divided by mod of W. Now here we can so since we want to maximize the margin, so without loss of generality, we can consider alpha equals to beta b plus 1 and beta equals to b minus 1. So when we get this, when we get this consideration in this total margin, so we get 2 by mod of W that we have to maximize, okay, or in other way we can write mod of W divided by 2, which to be minimized, okay. So when we get 2 by mod of W, which is to be maximized, or in other way if we write this mod of W by 2, which is to be minimized. Now to make this problem easier when we are considering the gradient, so we can take the squared form. So what is the squared form? So squared form is the half of this mod of W squared. Okay. So without considering the constraint, there is no meaning of minimizing this W. Okay. So we have to minimize the W and maximize the bias B subject to some constraint. Now, what will be the constraint? Now, the optimization comes with some constraint. Now, let us assume that the level for our classes are that means the for negative class we are taking -1, and for positive class we are taking +1. Okay. Now, when we classify the data points, we want the points belonging to positive classes to be greater than +1. Okay, that means if we look at this figure, then we can see that since this sample blue points are sample blue points belong to positive class, and these sample red points belong to negative class. Now uh, if we want to get the uh, blue points in the positive class region, that means we have to this W transpose X plus B should be greater than equals to 1. Okay, should be greater than equals to 1. So greater than positive 1. So here W transpose X plus B greater than equals to 1, and the points belonging to the negative classes should be less than -1. That is W transpose X plus B less than equals to -1. Okay. Now we can combine these two. We can combine these two conditions. Okay. And when we combine these two conditions, then we can express them as yi into W transpose xi plus b greater than equals to 1. Now why we are multiplying yi? Because since we are considering n number of training samples, and these training samples are found to be found to be uh, found to be in the supervised learning model. So therefore, they will have the class levels. That means the class levels will be associated with n number of training samples. So that is why we get the yi, which is multiplied with this constant. So we can get this. We can get this. We can get this dual problem, or the primary problem, in which B to be maximized and bias to be maximized, and W to be minimized subject to this constraint. Since here we are combining these two constraints, or these two conditions for positive class and negative class, and we can write them as a single constant, which is yi W transpose xi plus b greater than equals to 1. Okay. Now As I said that the optimization problem, this optimization problem without constant is meaningless. Okay, so since this optimization problem, we have to solve this optimization problem with some constant. So therefore, this half of W transpose W to be minimized subject to this constant yi W transpose xi plus b greater than equals to 1. Okay. Now, if we consider if we consider the negative class, for the negative class yi becomes minus 1. Okay, yi becomes minus 1, and here this wt plus b also negative. So this yi negative, this wt plus b also negative. So this becomes positive. When you multiply yi with this term, this becomes positive. Okay. So for the positive class, this also becomes positive. So therefore, the multiplication of this yi wt plus b becomes always positive. Okay, always positive. So that is why we are getting this constant as y w transpose xi plus b greater than equals to 1. Okay. As I said that the optimization problem, this optimization problem is called the primer problem, and it is guaranteed to have the global minimum. Now we can solve this by introducing Lagrange multiplier. Okay, so we are introducing Lagrange multiplier to get the extrema as minimum or maximum. Okay, and we can convert this primal problem into dual problem. That means we can convert the constant problem into unconstant problem, where the dual problem can be given by L of W comma B comma alpha. Here W is the weight vector, B is the bias, alpha is the Lagrange multiplier. Okay. Now, if we get the Lagrange multipliers, the value of the Lagrange multiplier for a particular training sample is large. That means we can give more importance of that training sample as support vector. Okay. And if we get the Lagrange multiplier alpha I for the ith training sample is 0, that means there is no importance of the training sample as support vector. That means that training sample is not found to be support vector. Okay, so they are non-informative observations. So when we get the Lagrange multiplier alpha I for ith training sample is large, okay, and that means the ith training samples any ith training sample is having more importance as support vector, and most probably that support that observation or that sample points become the informative as support vectors. Okay, and which are these support vector will be found on the decision the task boundary or the hyperplanes which are parallel to this the optimal hyperplane or separating hyperplane. Okay, now this dual problem is given by this equation L of W comma B comma alpha, which is given by half of W transpose W, or we can write W dot W. When we write in terms of dot product, then just we will write half of W dot W and minus summation over this alpha. This alpha is the Lagrange multiplier yi into W transpose xi plus b minus 1. Okay, so here you can see that instead of writing yi W transpose xi plus b greater than equals to 1, we can write equals to 1. Okay, we can write equals to 1, and if we take this one on the left hand side, then yi W transpose xi plus b minus 1 equals to 0. Okay, so that is why here we are getting this. So this will be multiplied with yi and yi and alpha, and over which we get this summation for n number of training samples. Now this is called the Lagrangian function. So this function is called the Lagrangian function of the support vector machine, and this Lagrangian function will be differentiable with respect to W and B. Since we need to get the we need to minimize the W and maximize B, therefore we need to determine the gradient with a gradient of this Lagrangian function with respect to W and B. So when we take the partial derivative of L with respect to W, we get this value for the W. So W is given by summation over alpha yi xi, and when we take the partial derivative of L with respect to B, so this will give us the gradient. This will give us the gradient of the Lagrangian function, and here we get another. Here we get the another constant, which is nothing but summation over alpha y equals to 0. Okay, for n number of training samples. Now, if we substitute this, two constraint in this Lagrangian function, then we will get the dual problem of support vector machine. Okay, dual problem of support vector machine. That means here we substitute the W in this Lagrangian function, and this dual problem will be solved subject to this constant. Subject to this constant, and this constant is determined when we take the partial derivative of L with respect to B. Okay. Now this dual problem is found to be easier to solve, since it has only the Lagrange multipliers. Okay, and the fact that the dual problem depends on the inner product of the training data that comes when extending linear SVM to nonlinear boundaries. Okay. So we saw SVM with hard margin where the misclassification is not allowed. Now, if we consider SVM with short margin, then here we allow the misclassifications to be happen, and here we can get the similar optimization procedure with some differences. The first difference is that here we allow the misclassification, and so when we allow the misclassification, we will need to minimize the misclassification error, and here we have to deal with one more constant. Okay, one more constant. So apart from the model loss function, so here we have to deal with one more problem, which is related to the misclassification error, which is to be minimized. Okay, and the second difference is that to minimize the error, we should define the loss function. The common loss function used for short margin is hinge loss. Okay, which is known as hinge loss. So hinge loss is defined as max of 0,1 minus yi W transpose xi plus b. Okay. So this is the hinge load. So among these two values, we will take the maximum, and this maximum will give us the value of the loss function. Now the loss of the misclassified point is called the slack variable. What we call the slack variable. Okay. Now what is slack variable? So slack variable is defined as GI. GI means for ith training sample, we get this zeta I, and zeta I here is the slack variables. That means when some misclassification is done, then we get this slack variable, corresponding slack variable, and this slack variable is added to the primal problem. So this was our primal problem. Now we are adding this slack variable with another regularization parameter C. Okay. So this regularization parameter, here we can get the primal problem. The first term is represent the primal problem, and with this primal problem we add the regularization parameter and the summation over this slack variable. Okay, subject to constant yi w transpose xi plus b greater than equals to 1 minus this slack, this zeta I. So here I varies from 1 to n. That means for n number of training samples, we can get this n number of slack variables. So if a subset of observations, non subset of observations are found to be misclassified, then for those misclassified observations we have to minimize the error. Okay, and for that we get the slack variables, and these slack variables slack variables to which the summation is to be computed, and this will be multiplied with the regularization parameter. And this regularization parameter C controls the trade-off between maximizing the margin and minimizing the loss. So in this diagram here you can see that since here the blue points belong to the positive class and red points belong to negative class, here you can see that some observations or some points from positive class are found in negative class region as well as within the boundary. Okay. Similarly, here you can see that one observation from the negative class is found within this margin between two hyperplanes, which are parallel to this optimal hyperplane or separating hyperplane. So that means for these points we have to get the slack variable. For these points we have to get the slack variable, and for these points we have to get the slack variable. Okay. So this slack variable to be computed and to be multiplied with the regularization parameter. Okay, and this regularization parameter basically trade-off between maximizing the margin and minimizing the loss. So at the same time, this regularization parameter tries to maximize the margin between these two hyperplanes, which are parallel to the separating hyperplane, and minimizing the loss. Okay. Now considering this slack variable, if we uh, if we try to solve the dual problems, then the dual problems will be defined as minus half of this double summation over alpha I, alpha j, yi, yj, xi transpose xj plus this summation over alpha I. Okay, subject to this constant. Here alpha I will lie between 0 and c. Okay. So this for the short margin of SVM. So when we allow some misclassifications misclassifications in the SVM, then we get the short margin. Okay, and for this misclassification, we get the slack variable, and we can define the dual problems by considering the slack variables with regularization parameter. Okay, so here here we can see that here we found that the hard margin and the margin in SVM lies in the separability of the data. Now, if our data is linearly separable, we go for the hard margin. That means here we do not allow any misclassification. However, if this is not the case, then we will get the short margin, and in the short margin we will allow some misclassification. Okay. Now, sometimes the data is linearly separable, but the margin is so small that the model becomes prone to overfitting, okay, or being too sensitive to outliers. That means if the data is linearly separable, but the margin is so small, then we will get the overfitting problem. Or if it is not overfitting, then there will be some outliers, and these outliers will be found to be very sensitive to the separating hyperplane. Now, in this case, we can opt for a larger margin by using margin SVM in order to help the model generalize. In order to help the generalize the model better. Okay, so in practically we get the misclassifications in the classification problems, and for that we have to opt the short marching of the SVM in order to help the model to be generalized better. Now suppose we have been given a function f of x comma y comma z, now for which we want to find the extrema. So here extrema means extrema may be minima or extrema may be maxima. Okay, subject to some constant. Here the constant means the condition. So here condition is given, and subject to this condition or subject to this constant, we have to find the extrema of this given function f. Okay. Now the idea used in Lagrange multiplier is that the gradient of the objective function a, gradient of the objective function f will line up either in parallel or anti-parallel direction to the gradient of the constant g at an optimal point. Okay. So in both direction, either in parallel or anti-parallel direction to the gradient. Now in such cases, one of the gradient should be some multiple of another. Okay. So here you can consider a problem. So here the problem is that here we have been given the given a function f of x comma y equals to 8x square minus 2y, and this function we have to find the extrema of this function subject to this constant x square plus y square equals to 1. Okay. Now using Lagrange multiplier, we can easily solve this problem. Okay, we can easily obtain the extrema of this given function f subject to this constant. Okay. Any questions from today's class? If you have any questions, you can ask me. Otherwise, we will stop now.
Okay, sir. No questions.
Okay, that's all for today.
Yes, sir.